So let's have another example. Draw the mirror image of the ribose. We are given the structure of the ribose. So to draw the mirror image, draw the vertical line and then simply draw the reflection. So your OHs are going to be on this side. Here you go. And then the hydrogens are going to be on the other side. Remember that everything on the vertical line stays the same. Okay, so you do have your carbon double bond O in there and the hydrogen. I'm just showing the reflection in there. And then you do have your CH2OH. Guys, remember that the mirror image of the D is the L stereoisomer in there. So that is going to be the L ribose. And again, this one is a D because the OH is to the right. Here, the OH is to the left. This is why it is the L stereoisomer in there. So now how many chiral centers do we have? Each one of those is considered to be a chiral center because each one has 4 different groups. So take each one separate and look at it. They have 4 different groups in there. So I do have 3 chiral centers in there. So that is going to be 3 chiral centers, okay, that I have. So now we're going to go ahead. We're done from the first part. Draw now the Haworth cycle. So to draw the Haworth cycle, it's very important to know how many carbons our monosaccharide is, because we know that we have either to make a cycle of 6-membered rings or a cycle of 5-membered rings in there. But if we don't have enough carbons for the 6-membered rings, then we do the 5-membered rings in there. But always we shoot for the more carbon cycle because it is more stable. Okay, so we're gonna follow the same rule in there. We're gonna start numbering from the top, always from the top of our monosaccharide aldehyde. So that is going to be 4. Guys, never number the CH2OH at the bottom. This one you just skip. Okay, so here once I reached 1, 2, 3, 4 in there, I had to make that oxygen number 5. So this means that I am stuck with a 5-membered ring cycle. 5-membered ring cycle is what? It is going to be a furanose ring. So over here I have my furanose ring in there. So go ahead and draw the structure of the furanose ring. So this is how it's going to look like. Let's draw it in a better way. So I do have my furanose ring, and this is how it needs to look like in there. Let's put it a little bit up so that I can have some space to put all of these substituents in there. So this is going to be my furanose in here. Go ahead and start your numbers. We said that this is always carbon number 1, okay? So that is always carbon number 1. If I want to highlight that, so this is going always to be carbon number 1. It's going to be the anomeric carbon in there. And then continue your numbering, move down. This is 2, this is a 3, this is going to be 4. And then you do have the oxygen, which is actually 5. So what you are making over here is you are going to use that double bond of the carbonyl, open it up in order to make a bond between the carbon 1 and oxygen 5, and the hydrogen on oxygen 5 will be picked up by this oxygen to become an OH. So this is actually what you are doing in there. Create the cycle, and this is the bond that you are creating between, sorry, it's not this bond over here. It is the bond between carbon number 1 and oxygen number 5 in there, okay? And then go ahead and follow the rule that all the groups that are on this side, those need to be up, and all the groups on this side, they have to be down in there, okay? So let's put them. And so on carbon number 2, we do have the OH pointing down. I'm just going to draw the OHs. I'm not going to draw the hydrogens. On carbon number 3, we have the OH also being down in there. Now on carbon number 4 in there, so what do we have? Yeah, so on carbon number 4, we do have what? We do have a hydrogen in the CH2OH. Remember what we said about the CH2OH, that this one is always up. Now, where does it belong? It belongs to carbon number 4. So we're going to go ahead and put it up there, which is the CH2OH in here. Okay, so that means that this hydrogen is going to be down. Now, for the anomeric carbon in there, you do have two options because this carbon double bond O changes into an OH, right? So you do have two options. If you chose your OH to be up, then that is going to be called the beta anomer, and we're going to call it the beta D ribose. Since we went ahead and we drew the furanose ring for the D isomer. We didn't draw it for the L. Plus, we're going to put plus in there because we're going to draw that same thing in there with the alpha anomer. So over here, we're going to have still my OH pointing down, the OH here pointing down, the CH2OH. Okay, so if my OH over here points down, then in this case, that is going to be the alpha D ribose anomer. Okay, so this is going to be the Haworth structure in there, and the Haworth structure is based on how much carbons you can fit in the cycle. The rule says that the more carbons, the more stable is the monosaccharide when it cyclizes. So always a pyranose or a monosaccharide that forms a pyranose cycle is more stable than the furanose one. So if you're able to form a 6-membered ring, go ahead and do it. But here we can't. The maximum we can form is a 5-membered cycle structure, which is the furanose. So this is it. Let's have another example, the D-galactose. So D-galactose, these are aldohexoses. So get the structure from the table and write it down. Okay, so since there are 6 carbons in there, there's a big possibility that they can form a pyranose ring. These are aldohexoses, and this is the aldehyde functional group. So we are going to cyclize this, start numbering your chain. This is 4, this is 5, and the oxygen is going to be 6. We are going to form a bond between carbon 1 and oxygen 6 in there, and then the double bond O in here, we're going to allow this to change into NOH. All the groups that belong to this side over here, all these groups that belong to the left, these are going to point up. All of these groups here that belong to the right, these are going to point down. Okay, now because my total number of members here is 6, I can form a pyranose easily. We're going to start numbering always from the anomeric carbon. This is the anomeric carbon, so that's going to be carbon 1, 2, 3, 4. That is going to be 5, and the oxygen is 6. You are making a bond between carbon 1 and oxygen 6, so this is the new bond that you are making in this case. Now let's go ahead and put the groups. I'm just going to go ahead and draw my OHs in there. So on the second carbon, my OH is down. On carbon number 3, my OH is up. On carbon number 4, my OH is up as well. Okay, so that is going to be the OH. And then on carbon number 5, I do have the CH2OH, which is always up in there. So that is going to be the CH2OH. Guys, again, you can put the hydrogens in there. So now your hydrogen is going to be down. You do have a hydrogen that is down here, a hydrogen that is down, and a hydrogen here that is up. It is fine, but it looks more simple if you just keep it without the hydrogens there. And then on the anomeric carbon, your OH on carbon number 1 can either be up or it can be down. So if your OH is down, then that is going to be the alpha D galactose. Okay, and if your OH is up in there, let's keep the same groups there. So you have your OH down, up, and then the CH2OH, then that is going to be the beta D galactose anomer. Okay, both are going to form. Remember, guys, that this is the anomeric carbon. So this carbon over here and this carbon over there, both of those are the anomeric carbon. And this is where the orientation of the OH changes. And this is why we call those two stereoisomers, because you do have here the orientation around this carbon. It changes. In this case, the OH can either be down or it can be up. Now for fructose, this is the only ketohexose that we are going to consider. This is the sweetest type of monosaccharide. It is a fruit sugar. It is found in a 1-to-1 ratio with the glucose in honey, and it exists in both representation cycles as pyranose or as furanose. Of course, pyranose is more stable than furanose, so D-fructose is more represented as a pyranose than a furanose, but it also exists as a cycle of 5-membered ring. So we're going to consider both in this example in here. And for just a future reference, when I ask you to draw the Haworth structure of D-fructose, I will specify if I need you to draw the pyranose or the furanose. So in order to draw the pyranose in there, we're going to follow exactly the same rule as we did before. We're going to start numbering from the top of the vertical line in the Fisher projection. This is 4, this is 5, and this is 6. Now notice here, this is the Fisher projection for the fructose in there. And when you draw the Fisher projection for a ketone, this carbon over here is not a chiral center. It's simply a carbon with a double bond O. So here I do have 1, 2, 3 chiral centers only, because carbon number 6 is also not a chiral center. This carbon doesn't have 4 different groups around it. It has 2 hydrogens that are the same. So the only ones that are chiral in here, let's put an asterisk on those. These are carbons 3, 4, and 5. So here you do have 3 chiral centers in there. You have 8 stereoisomers. You have 3 chiral centers only. Okay? So whenever I want to do the cyclization here, I'm going to cyclize, of course, from the carbon of the carbonyl. So I will be making a bond, not from carbon number 1 as I did with the aldehydes. Please, guys, pay attention. I will be making a bond from carbon number 2 to the oxygen, and so I have here 5. This is 6, and oxygen 7 in there. Okay, so I would do a bond between carbon 2 and oxygen 7 in there. By doing this, count the number of membered rings. These are 6. So this is going to be 1, 2, 3, 4, 5, and 6. So don't be fooled by the number 7. You're not forming a 7-membered ring. Just subtract that one. You are forming a 6-membered ring in there. Okay, so this is the carbon of the carbonyl. Let's go ahead and highlight it. So that is the second carbon over here. We said always, always. This is going to turn into an anomeric carbon, you guys. So this carbon over here, I am going to put it there. It's always going to be here. It's not going to be carbon number 1, but it's always going to be here. Okay? So according to my numbering, this is the second carbon. So I'm just going to move. This is the third carbon. Always move numbering down like this. So it's a second. This is a third. This is 4. That is 5. That is 6. And this is oxygen number 7 in there. Now we're going to follow exactly the same rule. Okay. Because the double bond O opened up. They picked up the hydrogen from this OH in here. And they made a bond between carbon 2 and oxygen 7. So actually, it's this bond over here that is a new bond that I made. Okay? And carbon number 2 is the anomeric carbon. The rule says that everything that is on the side, it's going to be pointed up. Everything that is on the side over here, it's going to be pointed down. Okay, and I do care about those because these are the ones that belong to the chiral center. So on carbon number 3, I have my OH pointing up. Let's change this color, make it black. So I do have my OH pointing up on carbon number 3. On carbon number 4 in there, I do have my OH pointing down. On carbon number 5, I do have my OH pointing down as well. Now, on carbon number 6, what do I have? On carbon number 6, I have the 2 hydrogens in there. So I can simply keep it like that. Just don't put anything on 6. Or if you want, I can put the hydrogen here and I can put the hydrogen there. Okay, if you want. So I can either keep it blank, nothing. If I keep it blank, it's a CH2 anyways. And then you have oxygen, that is the oxygen 7 in there. We still have whatever is connected to carbon number 2. So whatever is connected to carbon number 2, this carbonyl turned into an OH. So it's an anomeric carbon that will have the OHs up and down, the alpha and the beta. And then I would have the CH2OH in there. So it depends on where is the anomeric, where is the OH on the anomeric carbon. If the OH is pointed down on the anomeric carbon, then the CH2OH, this is the CH2OH, is going to be pointed up. And this structure over here is going to be called the alpha D fructose. Okay, we're going to do the same thing in there. So you have your OH, and then your OH. This is carbon number 6, so we can leave it blank or put the 2 hydrogens like that. Oxygen 7. So if your OH is up, then the CH2OH is going to be pointed down in this case. If you keep those same numbering here, that is going to be carbon number 2. This is a 3, 4, 5, 6, and 7 in there. And this is going to be carbon number 1. And we're going to call this the beta D fructose. Okay? So fructoses, they do exist as a 6-membered ring pyranose. And that 6-membered ring is more stable than the 5-membered ring though. So let's go ahead and draw the 5-membered ring. Okay, so that is still the fructose in here. And we are going to use the same numbering. So that's going to be 1, 2, 3, 4, 5, and 6 in there. Now, since we are, since we are using the furanose in there, I do have to stop at 5. It's going to be 1, 2, 3, 4, and 5. Yeah. So I do have to stop at this carbon over here. And the oxygen is going to be 6. in there, so that I would make an interaction or a bond between carbon number 2 and oxygen 6 this way, and that is going to form a 5-membered ring. Start numbering from the second carbon, you guys, and that is going to be my anomeric carbon. We're always going to put the anomeric carbon over here. You are making a bond between carbon number 2 and oxygen 6, so that is carbon number 2 and oxygen 6 in there. And then continue the numbering. This is a 3, 4, and that is 5. And of course, on the second carbon, you do have an anomeric carbon, and that anomeric carbon depends. If the OH is down, then the CH2OH is going to be up, and so forth. So let's put the groups in there. You do have on carbon number 3, the OH is up. Let's change the color in there. So the OH is going to be up on carbon number 3. On carbon number 4, the OH is going to be down, and on carbon, that pretty much that's it. So that is going to be on carbon number 4. Yes, the OH is going to be down. Now on carbon number 5, what do you have? Now the 5 is connected to the 6. On the 5, you do have what? On the 5, you do have the CH2. So what is this? This is the CH2OH. And this is not a chiral center. It is a regular CH2OH in there. And that is on carbon number 5. So we're going to go ahead and put the CH2OH. And remember what we said, that the CH2OH is always up. Okay? So that is going to be up. And that is going to be the CH2OH in there, okay, and on the second carbon, I do also have the CH2OH in there. So if I chose my OH on the anomeric carbon to be down, then in this case, the CH2OH is going to be up, okay? So that is going to be my anomeric carbon in there, and that is going to be the alpha D fructose in there, okay? And if my OH is pointed up, then the CH2OH is going to be down, and then I keep the same orientation of the rest of the OH substituents in there. And of course, the CH2OH is always up over here, and that is going to be the beta D fructose anomer in this case. So it really depends where your OH is, and that is going to force the CH2OH, which is this one. Okay, so when you start here, if you want to follow the numbers, this is going to be 1, and that is going to be carbon number 1 in there. I am numbering as I am cycling it, okay? Because it's going to be 5, and that is going to be 6 in there. When you're doing reactions, you are going to start the number from the anomeric carbon. That is different. But whenever you are cycling the structure, always start your numbering from the top of the carbon chain in the Fisher projection. This is easier in order to cycle that compound. Let's have another example. So draw the pyranose Haworth structure of the following D-ketohaptose. So this is a random ketohaptose, which is made up of 7 carbons now. Okay, this is a longer monosaccharide. It's made up of 7 carbons. It is a ketone. So let's go ahead and cyclize that. And it's asking me to draw the pyranose structure. So see now, it's a specific. Whenever we are working with ketoses, we have to be specific whenever we want to draw the Haworth structure. Do we need the pyranoses or do we need the furanose? So over here, we're going to start our number. So that is going to be from the top of the vertical lines. This is a 3, 4, 5, and 6 in there. I need the pyranos, right? So I need a 6-membered ring. I know that my reaction is going to start from this carbon to the, in order to form a 6-membered ring. So let's go ahead and count. 1, 2, 3, 4. I need this 5 and I need this 6. Okay, so I need all of those, so that is going to be 7 and that is going to be 8 in this case. And what I am doing over here is I am simply making a bond between carbon 3 and oxygen 8. These numbers are to make it easier for me in order to put the cycle together. Okay, so if I go ahead and follow the numbers in this case, what I have here is going to be carbon number 3. That is going to be 4. This is going to be 5. It's going to be 6. That is going to be 7 in there. And that is going to be oxygen 8. Which makes sense based on my numbers. On carbon number 3 is going to be an anomalic carbon. So I'm going to skip that for a moment. Now on 3, I have this whole group in there. Let's go ahead and put the substituents. So on the side, everything here, it's going to be pointed up. Everything here, it's going to be pointed down. And these are going to be my chiral centers. These are 4, 5, and 6. These are my chiral centers in there. So here you go. On, let's see, on 4. So on 4, I do have my OH being up, so that is going to be OH being up on 4. Same thing for 5, the OH is going to be up there. On 6, again, the OH is going to be up. Now on 7, what do I have? On 7, I do have the CH2OH in there, which is always going to be up, so that is going to be the CH2OH in there. I will skip the hydrogen on 7 in there. If you want to show it, you're going to show it down, okay? And then pretty much, yeah. So you can, if you want, you can show your hydrogens in there. It's not a big deal. It just makes the structure just more complicated. And on carbon number 3, if you chose your OH to be down, then this whole group that you see over here, okay, this whole group that you see, it's going to be up. Just to draw it as is. Don't make it complicated. Just to draw it as is. So the way that I would see it, what do I have? I have a CH, and that CH is connected to an OH in there. So you have the CH connected to an OH, and then the CH2OH, and then the CH2OH in there. Okay, so if you want to go ahead and start the numbers, that is going to be carbon 1, that is going to be carbon 2 in there, and then you have your carbon 3, and then as you go. Okay, of course, plus the beta anomer. And the beta anomer is the same thing, but here you gotta reverse it. So the OH is gonna be up and that whole group is going to be down. This is called the alpha, it's a D, and it's a keto haptose. So it's a keto and it is a haptose. Just a side note in here that we cannot form more than a 6-membered ring, no matter how many carbons the monosaccharide is. The maximum number of carbons that we can form to have a cycle is a 6-membered ring.